the second sections is diffusion in crystal lattice. So we are going to show you how the atoms jumps in crystal lattice. So the first part will talk about there are 4 different diffusion mechanisms, including the ring mechanism, vacancy-mediated diffusion mechanism, interstitial mechanism, interstitial C mechanism, and we also will give you some real examples and tell you how to estimate the diffusivity in vacancy-mediated FCC structures, or how to estimate the diffusivity in interstitial diffusing mechanism in BCC structures. And at the end of this part, we are going to talk about the atomic diffusion in ionic solids. So here we are going to introduce the vacancy mechanism, which we have 2 different kinds of vacancy, or vacancy defect we call a Ch4 and Frankel defect. And also in ionic solids, we are going to tell you the extrinsic and non-stoichiometry effect, which will affect the atomic diffusion in ionic materials. So let's move to the first part. But no matter which one, the final goal actually is get the self-diffusivity D star in different kinds of diffusion mechanism. We hope you can obtain the D star in different diffusing mechanisms. Okay, so the first one we are going to introduce you is we call the ring mechanism. So we have the host atoms in black, and now there's a diffusing atom in blue. So what's the ring mechanism talk about? Actually is a diffusing atom at substitutional site exchange with a neighboring or nearby atom by cooperative ring-like rotational movement. So the diffusing atoms move to right-handed side, and in the meantime, the host atom move to the left-handed side. They move together. But this kind of movement will cause the diffusing atoms moves from here to here, right here to here. Diffusion happens. But this kind of diffusion mechanism, they move together, so that will cause the high lattice distortion energy. Due to the high lattice distortion, so that tell you that it's not an energy favorable process. So that implying that this diffusion mechanism always happens in high temperature, because at high temperature, the atoms always have higher energy, which can overcome the higher energy barrier due to the high lattice distortion happen in this kind of happen in ring mechanism, right? But some people probably will ask, how about if we can lower the lattice distortion? Does that imply that the probability will increase? That means this ring mechanism will more easily happens. Yes. But how to lower the lattice distortion? So probably some people will say, oh, how about there are more atoms move together? Yes. If there are like 4 atoms move together, let's move to here, and so on. So 4 atoms move together. Yes, that will cause the last lattice distortion on surrounding atoms, but the probability of this events is quite low, because you are going to at the same time, these 4 atoms is going to move like this directions. the probability of this event is quite low. So let's move to the second diffusion mechanism. Actually, we call it a vacancy-mediated mechanism. So we also have a host atom in black, and there's a diffusing atom in blue, and you can observe there's a vacancy here. There's a vacancy nearby the atoms. So the diffusion atom at substitutional site exchange with a neighboring or nearby vacancy through atomic jumping process. So this kind of jumping process also will cause the lattice distortion, but this diffusion mechanism will depend on what? Depending on two things. The first one is the vacancy concentration and the atomic migration energy. So regarding to the vacancy concentration, as you know before, we know the concentration of vacancy is proportional to exponential minus vacancy formation energy divided by kT. And regarding to the atomic migration energy, as long as we know the atomic jump rate, or some people call it mobility, is proportional to minus migration energy divided by kT. So this vacancy-mediated mechanism actually only happens on there's a vacancy nearby, then these atoms can overcome the energy barrier. So it will be, you need to satisfy these two events. So you use the cross. You times this with this one. So you will get the diffusivity is proportional to exponential term, and within this exponential term, this delta H included the vacancy formation energy and atomic migration energy. So this is sum of vacancy formation energy, atomic migration energy. Okay, so let's give you an example for vacancy-mediated self-diffusion in FCC. Okay, so first of all, the question here, can you write down the self-diffusivity of the atoms here? So first of all, FCC, so I will write down the two unit cell of FCC. So you got the 8 corners and 6 atoms at the center faces, right? And we just copy the diffusivity as a function of gamma, mean square jump distance, and F, correlation factor. So we use based on this equation, we try to write down the diffusivity. But here is a vacancy mediated, right? So we assume the vacancy is located here and here at the on this plane. The center faces here, there's a vacancy. So here, the diffusivity can be expressed like a self-diffusivity. This is mean for the atoms. So we call D star is a self-diffusivity, so for atoms. And we also can get the dV is the diffusivity for vacancy. So based on the equation we grab or derive from previous slide, you got the gamma atomic jump rate of atom times the mean square jump distance R squared over 6 times the correlation factor F. The same thing can be expressed in dV is gamma V total jump rate for vacancy R squared divided by 6 times F. So next, in order to get the Z, because this is the total atomic jump rate, right? So you need to know the correlation factor or coordination number. Coordination number Z and gamma prime is the atomic jump rate. It's a jump rate in specific direction. You need to know the Z. For FCC, actually, the coordination number is 12. So how to get the 12 is if you focus on this vacancy, the nearest location at nearest atoms at substitutional site is there are 12. nearest atom, right, is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 9, 10, 11, 12. So it's a 12. And there is the distance to the nearest atoms at substitutional site will be expressed like this. So this is R. So the self-diffusivity can be expressed like the gamma A prime A squared F. So you can write it down something like this. So gamma A is 12 gamma A prime. Sorry. And you times the R squared, so be R squared. This is R squared. You times the F and divided by 6. Then you will get this results. Okay. Okay. So the vacancy part, you use the same vacancy, same idea, right? The vacancy also, the Z is 12, right? And so it's a 12 gamma V prime, and gamma V prime actually is the atomic jump rate or vacancy jump rate in specific direction, and you just this vibration frequency times the probability of crossing the barrier, right? We mentioned that in previous slide, in first slide of this lecture. So you can express like a gamma V prime A squared F is the same thing, just change the A as V. So we deal with this one. Vacancy, as we mentioned, vacancy can go anywhere, right? Can jump or exchange the location with any nearest atoms at substitutional site. So F equals to 1 is some kind considered as a random walk. It's a non-correlated jumps. But however, the atoms are not, right? Atoms can only jumps when there's a vacancy nearby or surrounding it. So the gamma A prime, the atomic jump rate for atoms is limited by XV is a concentration or atomic fraction of vacancy times the atomic jump rate for vacancy in specific directions. So it's limited by the concentration of vacancy and also times the gamma V prime. So here, you know there's a relationship between the self-diffusivity of the atom and the diffusivity of vacancy can be expressed like this, because this is the dV, right? So this is dV, so XV dVF. So we know the self-diffusivity of the atom equals to XV atomic fraction vacancy, diffusivity of the vacancy times F. So I will ask you, self-diffusivity D star and dV, which one is larger? Which one is dV, right? The diffusivity for the vacancy is larger than self-diffusivity of the atom, right? Because XV, the atomic fraction of vacancy, definitely is very, very small in your materials. So dV must much larger than D star. So anyway, so we assume this is under the thermal equilibrium condition. So based on this, you can get the XV can be expressed like the exponential vacancy formation energy divided by KT. Then you can separate them into temperature independent term and temperature dependent term. G equals to H minus Ts. So H minus Ts and T, you delete the T, so you get the entropy term here. So this is the temperature independent term, and this is a temperature dependent term. So now you can rewrite the self-diffusivity as XV becomes here, and dV here is what? dV here is A squared gamma V prime is here, so you can get here, and also F here. So here I just arrange them into the first term is temperature independent term, and the second term is temperature dependent term. So sometimes or in most of cases you can see like D equals to D0 times exponential energy term divided by KT is the temperature dependent term. And what's the D0 means? Actually it means included the D0 star actually included the correlation factor, lattice constant, vibration frequency, and also the exponential entropy term. And the second term actually we call it the temperature dependent term. The energy part in this case is included the vacancy migration energy and vacancy formation energy is E. So E included the vacancy formation energy and vacancy migration energy. Okay, so have any idea how to get the E in this energy term for your materials? How to do that? So you can measure the self-diffusivity at different time or different temperature. For example, like 5 different temperature, then I measure the self-diffusivity of these materials or in these materials. Then you can do what? You can, as long as you have diffusion, you can have a log D star as a y-axis, and x-axis would be what? 1/T. Then you have 5 data, right? So 1, 2, 3, 4, 5. Then the slope, got a slope. So maybe I can draw. Then the slope will be what? We got the fitting, the slope will be negative E divided by K. So K is a constant, so I can get the E. So this is how you can get the E for your materials. You just measure the self-diffusivity at 5 temperature. Then plot this figure and fitting, then you can get the E. And E actually included the vacancy formation energy and vacancy migration energy. Okay, so next slide is try to help you to determine the vacancy formation energy and migration energy for the vacancy-mediated self-diffusion in FCC. So how to get the vacancy formation energy and migration energy? At the thermal equilibrium, as you know, the vacancy, atomic fraction of vacancy can be expressed like the numbers of vacancy divided by the numbers of atoms, right? And be precisely actually is equals to what? Is equals to NV. Atomic fraction is NV plus N plus NV, right? But as we know, the NV is much larger than NV, so it becomes here, right? Okay, so this is so NV over N. Can we measure this one? The atomic fraction of vacancy, can we measure that? Yes, you can do that. How to do that? The most important part will be how can measure the atomic fraction or vacancy fraction in your materials. So here, the answer probably is you can try to heat your materials up and in situ measure the thermal expansion in the length, in the diameter, and you minus the increase in lattice constant, then you will get the residual part will be the contribution from the increase of vacancy, numbers of vacancy. Because as long as you heat your materials up, you can observe the thermal expansion effect, right? And this expansion is come from two reasons. The first one is the numbers of vacancy increase, yes. And the second reason is come from the increase of lattice constant. So as long as you got the delta L, the total increase in length over L, and you minus the contribution from the lattice constant part, then the residual part will be from the vacancy part. And this is we use the length, right? So it belongs to one dimensional. So you times the 3 to represent the three-dimensional cases. So thermal expansion, you can measure that in SEM. You can measure the delta L over L, and lattice constant part you can measure by XRD. So in your experiments, you can when you heat your sample, for example, you heat your sample to 300 degrees C. In the meantime, you wait until it reaches the thermal equilibrium. Then you in situ using the SEM to measure the length of your materials, and also use the XRD to check the lattice constant, whether the lattice constant changes. Then you can get this curve, delta L over L and delta A over L as a function of temperature. Then you can get this relationship, right? But how to get this relationship? You take the log, and the slope will become the vacancy formation energy. So as long as you have the NV over N, this results, and this atomic fraction for at 5 different time temperature, then take a log and versus log this value as a function of T over 1 over T. Then after fitting, the slope will become the vacancy formation energy minus vacancy formation energy divided by K. Then you can get what's the vacancy formation energy. And as long as you know the vacancy formation energy, and as we mentioned, you can get the delta E by measure the self-diffusivity as a function, or measure the self-diffusivity at different temperature, right? For example, like 5, you measure self-diffusivity at 5 different temperatures. Then you plot log D over T over 1. Then the slope you can get is you can simply get the delta E. So this you know, so you can get the vacancy for migration energy for your materials. So this is how we determine the vacancy formation energy, vacancy migration energy, and also the total energy for your materials. And this is just a quick review to explain why the lattice constant, there's always a increase on the lattice constant while you increase the temperature. So obey, this is the energy as a function of the distance between these diatomic atoms. So if it is ideal harmonic models, then you can observe the curves, the energy as a function of R will become like in green. So the N equals to 0, 1, 2, 3, 4, 5 means that when you increase the energy, then you can observe that the R, the distance between the centers of two atoms, keep the same with increased energy. So this doesn't make any sense because usually when you heat your materials up, you can observe the thermal expansion, right? So that's implying that this harmonic models is not exactly right or correct. So there's a modified model we call a Mohs model. Actually, is in blue. It's implying that when you increase the energy, the atoms might vibrate. The atoms always like vibrate. So if you write down the R, the average, the middle of the R, actually increase. So Mohs model can well describe why the lattice constant increase with increasing temperature. Okay, this is just a quick review. So actually, we finished the vacancy-mediated diffusion process and tell you how to calculate the self-diffusivity in these cases, and also how to determine the vacancy migration energy and vacancy formation energy in this system. And let's move to the third diffusion mechanism, which is we call the interstitial diffusion mechanism. For this case, we have host atoms in black, and also we have the small solute atom in blue. And this interstitial diffusion mechanism only happens when the diffusing atoms is quite small, so that will allow this diffusing atoms at interstitial site, and this atom is going to move through interstitial sites. So definitely this diffusing atom is small, so the lattice discussion is small also. So the interstitial atoms migrate between two interstitial sites. Diffusivity as a function of exponential term, and we think that the energy term is only involve the migration energy of these interstitial atoms. And also because the diffusing atoms is small, so you can expect it, the lattice distortion also with a lower lattice distortion compared to vacancy-mediated one. Okay. And diffusion activation energy is associated with the lattice distortion energy, which is we call it as migration energy M. Okay. And also, this expression tells you the D0 actually in D0 actually is the temperature independent term included the lattice constant, vibration frequency, and entropy term, right? And this term actually is temperature dependent term, so we have enthalpy, and this enthalpy is migration energy is associated with the lattice distortion due to this kind of atomic jumping process through interstitial size. Okay, so before we give you some real examples, let's take a look on interstitial. Introduce you. We do have two different kinds of interstitials in BCC. This is a BCC symbol. It's a unit cell for BCC. You got the atoms at the center of the unit cell, and also we have 8 atoms at corners. And you can observe the interstitial, we call it ultrahedral interstitial here. This is ultrahedral. This is located at the ultrahedral structure, so we call it ultrahedral interstitial. And also at the center of the plane, and also onto the middle of the edge. So this we label it in white. All this belongs to ultrahedral interstitials. And the other type of interstitial site in BCC, actually we call it a tetrahedral interstitials. Actually, you can observe this it is at the center of octahedral structures. So we call it as octahedral interstitials, and we label it in white as well. Okay, so let's give you a real example. Let's take a look on interstitial diffusion in BCC. We have a BCC here, and the interstitial diffusion actually here is we assume the solute atom or diffusing atom moves along octahedral interstitial site, which we labeled in white. And also we copy the equation we derived in previous slide. Its diffusivity can express like this. So in order to get the Z, so we put more efforts on this plane. This red cross is labeled octahedral site, interstitial site, right? So in order to determine Z actually is a possible jump direction for these interstitial atoms, so we need to label the available interstitial site, which is nearest to this interstitial atoms. So it's 1, 2, 3, 4. It's the nearest one, right? And with a distance A/2. And some people probably ask, how about this? We still have interstitial, but it's far away. It's longer than this distance, right? So the possible jump directions or jump site or possible jump directions is only happens to the nearest interstitial site. So the first we need to consider is how many sites which is nearest to the our target interstitials. So here in this case, if you consider these interstitial atoms, we only have 1, 2, 3, 4 possible jumping directions. Okay, with nearest distance is A/2. So the Z here is 4. So it's a 4 gamma prime. So gamma prime is a vibration frequency times the probability of crossing the energy barrier. So diffusivity can be expressed like a 4 mu. This is the Z gamma prime. And small r actually is the distance jump to nearest interstitial site. So it's A/2 square. So we got this one. And as we mentioned, there's no limitation to this interstitial atoms to jump. It can jump either this direction, and this jump is nothing related to next jump. So the F is equals to 1. So you got the diffusivity for these interstitial atoms, and also we separate that into temperature independent term and temperature dependent term. So we can find that this HM is the E. So this is a migration energy. This is associated with the lattice distortion. When this lattice distortion due to the atomic jumping process, right? Okay, so today that's ended